Sorry.
All right, no problem. Thank you, Elna. And thank you to the organizers for inviting me to this conference, this workshop, and my sincere apologies that I cannot be there. I hope everybody's enjoying the CFA if you've come from somewhere else, but you definitely don't want me there today because I've had a nasty bout of COVID for the last couple of days. So I want to talk about one particular phase of the multi-phase CGM, and again, I don't think we need to motivate the fact that the CGM is multi-phase. We've got plenty of evidence for that, all different wave bands. But for massive galaxies, and here I'm just saying massive galaxies with Milky Way mass and above, a significant portion of the CGM is hot and emits an X-rays. And yet we know very, very little about this phase, which is very important and possibly dominant in some of those massive galaxies. And that's because of just the limitations of our current instrumentation. So we cannot detect or analyze the hot CGM in emission, except maybe the innermost parts of massive nearby galaxies or in stacks, as we've recently seen with Rosita, without high spectral resolution. And the reason is, of course, is that we live in a massive enough galaxy to have its own X-ray emitting CGM. And for galaxies that are nearby enough to have a close, detailed look at their structure, the lines from the emission lines from those galaxies are simply overwhelmed by the Milky Way CG lines at CCD resolution. So if you look at that spectrum to the lower right, you'll see that's the best we can get as far as X-ray CCD resolution. That's the green curve there. So the lines that you see in blue, which are the Milky Way CGM lines in X-ray, basically just overwhelm the lines from the source, which are the lines that you can see in red from this redshifted this galaxy at cosmological redshift of 0.01. So the Milky Way and these other galaxies, needless to say, same physics, emit these same atomic transitions. But if you have an instrument, if you have an X-ray IFU that has high spectral resolution, at least like a few electron volts at most, and even better if it's 1 or 2 electron volts resolution. It allows you to distinguish between the emission lines between the source and the foreground if the source is cosmologically redshifted. If you can get those distant source lines to appear from behind the Milky Way ones, and the different lines reveal different phases of the sort of sub-phases, if you will, of the hot phase. So the oxygen 7 lines, could give you a hint of the full extent of the gas halo, whereas the hot gas halo, whereas the oxygen 8 reveals more of the hotter inner structure and possible influence by Rosita/Fermi bubbles like we see in our own galaxy. And then the iron 17 lines reveal the hottest gas. Of course, if you can measure lines to high precision, you can also measure kinematics, which I'll show very shortly. So the instrument that we proposed to the NASA APEX call, which we're going to hear about the first results from in the next month or a couple of months or so, is the line emission mapper. It's an X-ray integral field unit microcalorimeter. So it's the same genre of instrument as the CRISM Resolve instrument, which you may have heard of, but it is designed to be optimized for the CGM and the IGM and other X-ray sources in the lower energy, softer X-ray band. So it has a much higher effective area than current instruments. It has a PSF of 10 arc seconds. The field of view of the main outer array, which is the thing you can see there in magenta-ish, the hexagon there, with 2.5 eV spectral resolution. That field of view is half a degree, and this is large enough to map surface brightness in temperature out to the virial radius for a Milky Way mass galaxy at Z of 0.01. That's just a reference point. And then there's also an inner array with twice as high spectral resolution, and it's that purplish rectangle square in the center of 7 arc minutes, and that gives you the ability to map velocities and measure abundances and temperatures in different phases with high precision in the inner CGM. So we've done a lot of explorations over the past year as to what you could do with an instrument like this. So one thing is that a key is to distinguish between different modes of different theoretical explorations of AGN feedback in the simulations, which is the key difference between a lot of these simulations. And some of these models drive fast explosive outflows under winds, others more gently heat the gas, some emphasize supernova feedback, some emphasize supermassive black hole feedback. And what you can discover if you make these mock observations that you're seeing here and look at the CGM in the narrow lines that you can only do with an instrument like LIM is that this produces changes in how much hot CGM is retained, as well as how isotropic or anisotropic it is. And even though we emphasize emission because we are the line emission mapper, we can also do absorption. In each one of these very large 30 arc minute pointings, you're going to get lots of X-ray point sources, X-ray distant AGN and quasars, which you can use to do absorption line pencil beam studies and study the CGM in that way out to large radii. And just the last paper I want to mention is this recent paper from last year where we used galaxies from the TNG50 simulation that are all Milky Way-like. They're spirals. They all exhibit cavities like the Fermi-Rosita bubbles seen in our own galaxy. And you can look at these in other simulations, and you've already seen Emily Silich's talk today for an extension of the simulations of this work. But you can make predictions from the simulations for what you might see in X-ray. So you can see here, if you're looking edge on, you can see X-ray surface brightness in the top center panel there. You can see evidence of the cavities being blown by the AGN feedback. You can see the heated gas in the temperature in the top right. And in the bottom left, you can see the differential rotation of the hot CGM. And in the bottom center, you can actually see the velocity dispersion, which gives you a sense of like both turbulence of the gas and what it looks like along the sight line. Thank you, Elna. And so if you are, instead of looking at a galaxy edge on, if you're instead looking at like one that's slightly tilted, you see mostly the same story, but you can also tell, if you look particularly at the bottom left, you can see that what this strange looking map here is actually a combination of the AGN outflows moving perpendicular to, moving outward perpendicular to the gas disk. And that velocity is being projected along the sight line along with the rotational velocity. So you're seeing evidence for both rotation and AGN outflows in the bulk velocity map down there on the bottom left. And if you look face on, of course, in an idealized case where a lot of the velocity structure cancels out, but if it's turbulent, you do see a lot of structure, and you can actually discern the presence of the oppositely directed outflows in the velocity dispersion map, which you get from measuring line widths at the bottom center there. So these are just some mocks looking at an example of a single galaxy. This is oxygen 8 emission from Milky Way mass type galaxy, edge on the left, face on the right, and we've just broken this up into these little regions where we're extracting X-ray spectra and fitting them to models and analyzing them. These are what the spectra look like. The CGM overall is multi-phase, but the hot phase as I've mentioned already, has a very complicated structure that is not usually captured by single-phase models. So we definitely need multi-phase models just for the source itself, in addition to being able to model the foregrounds and the backgrounds adequately. But once you do all that, what you can do is that you can actually fit and recover, as you can see on the left, if you're looking edge on, you can actually recover the hot CGM rotation curve. The blue line is the result of the fit, and the orange line is the actual information from the simulation. And if you're looking face on, and if you use a multi-phase, multi-temperature model, you can actually discern different phases, and you can actually discern in the velocity dispersion that the velocity dispersion or the line width is coming from it's coming from outflows from opposite, it oppositely directed outflows coming out from the AGN feedback. So these are things that you could actually measure and distinguish using an instrument like LEM. So the last slide here, since I see Elna has come back to the screen, is it's called a line emission mapper, and with this technique, you will not be only able to map surface brightness, as you can see in this mock from a TNG galaxy to the left, and see the cavities. You can also map the temperature, and you can also map the velocities, as I've already showed. So it gives a whole new window onto the hot CGM of galaxies that's not been possible before. So that's my summary, and I'll take any questions you have.
Any questions for John? Because people don't want to stand up, I can repeat the question. Is that the limiting factor?
In the earlier plot you were showing where you're comparing TNG, Eagle, and Simba, what halo mass was that looking at?
A good question. And so I don't remember the exact number off the top of my head, but most of the galaxies we've looked at for this were roughly Milky Way mass galaxies or slightly above.
Okay.
So this is roughly between 1 and 2 times the mass of the Milky Way is roughly the mass range you're looking at here.
Cheers.
Yo, Jesse, quick.
So with LEM, would you be able to show Jake whether or not at redshift 2 galaxies have a hot outflowing CGM or not? More likely.
That's a good question. So we haven't done those. I haven't done those calculations, but so the thing I'm thinking more about is the angular scale, whether or not you could resolve the, how much you're resolving on in terms of angular distance, but so I don't have a good answer to this question right now, actually. I sense there's some people in the room that might be able to answer that question. It also depends on whether or not the lines you're using to measure it are within the LEM band at a redshift of 2. And the LEM band is roughly...
Satisfied with the reply.
Yeah.
Let's thank John again.
I'm not satisfied with my own reply, but...